Hi everyone. Today we're going to be learning about series resistance. That is, we're going to be learning about the effective resistance or total resistance of multiple resistors that are in series with one another. We're also going to learn about the effective voltage drop across a series of resistors. So let's look at two resistors that are in series with each other. In this case, we have R1 and R2. We can see that they're joined together like links in a chain, which means that they're in series. Now the combination of the resistors has a greater resistance than either resistor on its own. So if we put R1 and R2 together, then their combined resistance will be greater than R1 and it will be greater than R2. So the resistance of the combination of them is the sum of the resistances. That means if we want to find the total resistance of R1 or R2, that is to say, the effective resistance of the combination, then all we need to do is add the resistances together. Now, this relationship will stay true for any number of resistors, whether we have 2 or 3 or 6, all in series with one another. So if we have a set of resistors in series with resistances R1, R2, R3, R4, R5, and so on and so forth, then we can say that their total resistance is given by R1 plus R2 plus R3, and so on and so forth. In mathematics, we can also represent this by something that looks a little like this. And what this means is the sum of R with little k, where k starts at 1 and ends wherever. So the total resistance is going to be R1 plus R2 plus R3 plus R4 plus R5 and so on until we reach the last resistor that's in series. So once we know the resistance of a series of resistors, which we're going to mark with R total for total resistance, we can figure out the current through them, right? So Ohm's law, which we've dealt with before, says that the current through a resistor is V equals IR. So if we have a supply voltage and we have the total resistance of all the resistors in series, then we can use this to figure out the current through them. So we substitute V for the supply voltage and substitute R for the total resistance, and that gives us a figure for I. Now for a set of resistors in series, the current is constant. That means by finding the total current through the series of resistors, we find the current through each one as well. So the same current will flow through each different resistor as long as they're in series. Now we can use this current to help us calculate the voltage drop across each resistor. Remember that when a voltage is applied to a circuit, the voltage after each circuit component will drop a bit. It'll start up with the full difference between the two potentials that the supply voltage sets up. So if we have a 12-volt power supply, then the potential difference between the outgoing wire and the incoming wire for the power supply will be 12 volts. But as the voltage passes across each resistor, it'll drop down. So there'll be 9 volts left, then 6 volts left, then 3 volts left, and then back to 0 when we reach the terminal again, right? So Ohm's law will help us calculate the voltage drop across resistors. We start off at a high potential here, and we end up at a low potential here, which means that the power source is probably right in the middle of these, and this is our voltage. The difference between the high potential, where the positive charges have lots of potential energy, and the low potential, where the positive charges have very small potential energy. So Ohm's law states that the voltage drop across a resistor is given by V equals IR. So after the high voltage goes across R1, it's going to drop lower. And here we'll have a medium potential perhaps. Once we pass through R2, we'll drop down to a low potential. Now substituting a resistor's resistance for R and the current for I in this equation gives us V, the amount that the potential drops over the resistor. Now to find the voltage drop across a set of resistors, all we need to do is substitute the set's effective resistance, right, that is the sum of their resistances, for R in Ohm's law. So for resistors in series, the total resistance is R1 plus R2 plus R3 and so on. And the current through them is always going to be the same. So V total, that is the voltage drop across all the resistors together, will be the current, I, times their total resistance. But if we expand this so that it's I R1 plus I R2 plus I R3, we end up with this bottom equation. The total voltage drop across it will be V1 plus V2 plus V3 and so on. So that means that we can calculate the total voltage drop across the circuit by adding together the voltage drops across each resistor. Now in a series circuit, the voltage drop across the circuit is the sum of the voltage drops across the resistor, right? That's what we've just learned. So if we have a voltage of 10 volts, then we can say that the potential will be 10 volts on one side and 0 volts on the other side. That means that the potential difference between the plus 10 and the plus 0 is exactly 10. Now, when the current flows through here, it's going to drop down 6 volts across the 3 ohms. So we have plus 4 volts left. So we can see that the potential difference between the plus 10 and the plus 4 is 6 volts. And the potential difference between the plus 4 and the plus 0 is 4 volts. So the total drop across the circuit, once everything's added up, will always equal the supply voltage. So the voltage drop across the 3 ohm resistor plus the voltage drop across the 2 ohm resistor must equal 10 volts. This will always be true no matter how we configure the circuit. So the potential, we can say, gets used up as it passes across resistors. Remember that the potential is a measure of how much stored energy the charged particles have. So we started with a lot of stored energy. It's let out when we pass through the first resistor. So now we have a lot less stored energy. And the rest of the energy is used up as we pass across the second resistor. That comes from our definition of how voltage works. At a high voltage, we have a lot of potential energy. It's like we're at the top of a hill. And as we pass through the circuit, it's like we're rolling down that hill and turning the potential energy into heat energy while we pass through the resistors. So let's go on to some questions.